This lecture is actually more of just a very long example problem where I'm going to show you how to determine the empirical formula using experimental data. So we're going to be combining all of the concepts that we've been talking about for the last little bit to solve one problem. So you're going to need to know how to do a bunch of different things. You're going to need to know how to find your products or your amount of products from a given amount of reactants. You're going to need to know how to do limiting reagents. And you're going to need to know how to convert between empirical formula and molecular formula. So we'll go over each of those step by step in this lecture, but if you need a bigger review, just go back to the other videos. So first off, let's start off with a problem. So we have a combustion reaction of a certain amount of, and I'm going to keep this really general for right now so that it'll work for everything, and then we'll do a more specific one. So we just have an unknown compound, and I've written that as CXHYOZ, just to keep it general. And anytime you have a combustion reaction, you need to know that that's combined with oxygen to form water and carbon dioxide. So we want to find the empirical formula. Now, obviously, we can't solve this problem. I didn't give you any numbers. I didn't give you really any real information, but this is the general setup, and so it's good to look at it from a very, very general standpoint. So if we have this combustion reaction, let's first start and look at where the carbons are. So where are all the carbons coming from and going to? The only place that carbon comes from here is what we call the hydrocarbon, the thing that we're combusting. The only place that the carbon goes to is the carbon dioxide. So if we're collecting data on how much carbon dioxide we have, we know that every bit of that carbon in that carbon dioxide came from the hydrocarbon, and that's really useful information. We can use that. Now let's do the same thing for hydrogen. Where does all of our hydrogen come from? That too all comes from the hydrocarbon. There's nothing coming in from anywhere else, so it's all from the hydrocarbon that we're interested in. And all of it goes to the water. So if we're looking at how much water we have, we can figure out how much hydrogen we have, which means we know how much hydrogen we started with. Also a very useful number. Oxygen's more complicated, and when we go to do an actual problem on this, that's going to be the one that is really the most problems for us to solve. So with the oxygen, it's coming from two places. It's coming from both the hydrocarbon and from the oxygen that we're using to actually combust the species. And then it goes to two places too. It goes to the water and the carbon dioxide. But notice, if we measure our water and our carbon dioxide, that doesn't tell us how many oxygens are in the hydrocarbon. It tells us how many oxygens are in the hydrocarbon and in the oxygen that we use to burn it. And so we're not going to be able to do that the exact same way. So we're going to be able to use the total amount to solve for this, and we'll do that in the example. That one's a little bit more complicated. So let's start in on our example. So here we're going to take tartric acid, which is the white powdery substance that kind of coats a lot of the sour gummy candies, in this case Sour Patch Kids, and we're going to combust a certain amount of it. And then we're going to see how much of each substance we have, how much carbon, how much hydrogen, and how much oxygen, and we're going to use that to solve for an empirical formula, and then we're going to use that to solve for a molecular formula. So our eventual goal here is to find the molecular formula of the tartric acid. And we're going to do that in a similar manner to what I walked through in the very generic reaction. So our goal for all of these is going to be get to moles. We need to get to our moles of carbon, our moles of hydrogen, and our moles of oxygen. That doesn't change from when we were doing molecular formula problems in other lectures. How we get there now gets a little bit more complicated. Let's start with our carbons. So we know that all of our carbons are from our hydrocarbon and that they go to our carbon dioxide. So now let's look in the problem and see what we know about carbon dioxide. I tell you that we have 14.08 grams of carbon dioxide collected. Now, that doesn't mean that we have 14.08 grams of carbon, it's carbon dioxide. So we need to actually convert this into carbon first. So we want to convert into moles because whenever you want to convert from one species to another, you need to do it in terms of moles. So we have grams of carbon dioxide, and we're going to divide by our grams of carbon dioxide on the bottom to cancel that out, leaving us with moles of carbon dioxide. This next conversion factor, perhaps you don't need to do. It's one of those conversion factors that if you need to do it, do it. If you just kind of know that this is how it is, you could skip writing it. But I'm going to write it just to show you. So we know that for every 1 mole of carbon dioxide, we also have 1 mole of carbon within that. And I think it's a good idea to write it, though it's not necessarily mandatory if you know the difference. That leaves us with 0.320 moles of carbon. And while that's the moles of carbon in the carbon dioxide, that we know that that has to be the moles of carbon in the hydrocarbon as well. So one piece done. Now let's move on to the hydrogen. The hydrogen is very similar. It all goes from the hydrocarbon to the water. So if we know how much water we have, we know how much hydrogen we have, and we know how much hydrogen is in the hydrocarbon. So we'll start with the 4.32 grams of water. From here, we can convert into moles of hydrogen. We have to be a little bit more careful with this one though. So the first piece is the same. We divide by our molar mass in order to get our moles of water. Now here, we need to make sure that we're careful about our subscript. There's 2 hydrogens for every water, not just 1. And so when we do our mole ratio, we're going to put 2 moles of hydrogen on top to every 1 mole of water on the bottom. And if you don't remember to do that, then the problem becomes wrong. And so from here, we have 0.479 moles of hydrogen. Now let's go on to oxygen. This one's the more complicated one. So here we have oxygens coming and going everywhere. We have it coming from the hydrocarbon, coming from the oxygen, going to the water and the carbon dioxide. We can't do the same thing that we did before. However, if we know our initial sample size, and we do, I tell you that it's the 12.01, we know that carbon plus hydrogen plus oxygen has to add up to 12.01 grams. We also know how much carbon we have and how much hydrogen we have, which means that all of the rest of it has to be oxygen. So we're going to take the information that we solved for on the previous 2 slides. I'm going to put those up there right now. And we're going to use that to solve for grams of each thing. The reason being is that our initial amount was in grams. So we know that if we have carbon and we have hydrogen, all the rest has to be oxygen. So we'll use the molar mass to convert into grams. So that initial 12-gram sample had 3.84 grams of carbon inside of it. And we can do the same thing for hydrogen. So that initial 12.0 gram sample had 0.484 grams of hydrogen in it. So now we can take our initial sample size, we can subtract off the grams of carbon and the grams of hydrogen, and we can get our grams of oxygen. So now we're almost there, because if we have grams of oxygen, we can also solve for moles of oxygen, and that's what we're aiming for. We want our moles of everything. So we take our 7.68 grams of oxygen, we divide by our molar mass, and we get our moles of oxygen. And now we have our goal. We wanted to get to moles of everything, and we have moles of everything. So now this becomes exactly like the problems on the previous lectures where we discussed solving for molecular mass, where we have moles of each, which means we can find a mole ratio, which means we can find the empirical formula, which means we can find the molecular formula. So this was just a very complex way of getting back to this same spot. Most combustion analysis problems will start out like this, though there are a couple of challenge problems and homework problems that are a little bit more complicated that you have to use some higher level problem solving skills for. But we'll let you play with those on your own. So let's keep going. We have our moles of each thing. So I've just copied those over from the previous slides. Now this doesn't look like it's a super easy thing to get a whole number ratio from. And so this one we definitely have to use our trick to get a whole number ratio. On our previous example, it was a little up in the air. You could kind of see it. This one, you're going to need your trick. So we divide by our smallest number. That will get us close to a whole number ratio. It doesn't always get us perfect. And in this case, it actually doesn't get us a whole number ratio. It gets us 1 to 1.5 to 1.5, which isn't a whole number, but it's close enough where we can see the whole number ratio now. So if we multiply all of those by 2, we get a nice whole number ratio, C2H3O3. And so this gives us our empirical formula. I didn't give you enough information on this particular one to check to see if this was also the molecular formula. It would just take one more step of experimental data where you then had your molecular mass. So for this one, we've solved the problem and can move on. So we went through and we combined many concepts, many sets of problems that we learned in different lectures into one complicated problem. This isn't a problem that you should necessarily memorize every single step, every single way to do it, but use the problem-solving type aspects of it to solve other problems like it.